The speaker is Professor Ruy Exel. He did his PhD from the University of California at Berkeley in 1985. His research interests are in operator algebras and in dynamical systems, and he works at the Federal University of Santa Catarina in the beautiful city of Florianopolis. Please, Professor Exel.
Thank you very much for the introduction. Thank you all for coming. This talk is based on ongoing joint work with Rodrigo Bissacot, Rodrigo Frausino, Thiago, Raszeja, some of them who are present here in this audience, and some even drove overnight to be here in this talk, so I'm very honored by that. And this is some work that we have started in March. In fact, when I was first invited to give this talk, I gave a different title, and you might notice that if you click on the paper on the app, you will be led to the old paper. So I'm sorry about that. The paper is already on the archive, and it's I think it appeared today in the archive, thanks to the efforts of the Paulista team. Okay, so let me begin with something very elementary and well-known, which is the discussion of the Markov subshift. So we start with a matrix, with a 0-1 matrix. So that's an n by n matrix in which all of the entries are either 0 or 1. And with that matrix, we build Markov space. So Markov space is the set of all infinite words in the alphabet of n letters, such that the matrix allows for the transitions, i.e., every time you see two adjacent letters here, then this corresponds to a pair of indices. And if you check the matrix has to allow that, meaning that the matrix entry is equal to 1. So if we look at the space, the finite space 1 to the n with the discrete topology, it's a compact space. So the product topology, and notice that sigma A is a subset of the product topology. Sigma A is compact by Tikhonov's theorem. So since sigma A is easily seen to be closed inside of sigma A, then sigma A is a compact space. So the space we're looking at here is a compact space. Markov shift is a well-known map on the space, which is very important from dynamical systems point of view, and it's simply the map that takes an infinite word and deletes the first letter from the word. Now, if we take a continuous function h on Markov space, this is usually viewed as a potential, and if we're given a positive number beta, which is viewed as an inverse temperature, then we can define a Ruelle operator on the space of continuous functions on Markov space by that formula. So that formula essentially is you take a function f, and we're making another function called L beta of f, which averages the function over the inverse images of the point x, of the point y. So the L beta f is computed at y here, and this is a sort of a sum in which the values of the function f are taken on the pre-images of y. And of course, there are these factors e to the minus beta h of x. So this is called the Ruelle's operator, and so we can then build the dual Markov operator on the space of Borel measures. So this is a trivial duality in terms of Banach spaces. So given a measure mu on sigma sub A, the dual operator builds a measure L beta star of me, which integrates according to this formula. So a function integrates against this measure by applying L beta to F and integrating against the original measure mu. So there's a fundamental problem in statistical mechanics to find the probability measures on sigma sub A such that L beta of mu, L beta star of mu is equal to lambda mu, i.e. These are eigenmeasures for the operator L beta star. And when lambda is equal to 1, and in which case we have a fixed point, then these measures are called conformal measures. So I should say that I'm not a specialist in this problem, and I might defer questions about this specific problem to my co-authors here present. And I am going to go to a different direction towards C-star algebra. But let me at least say that the existence and uniqueness of conformal measures depends very much on the matrix A, which is usually assumed to be irreducible, and the regularity of the potential H. The potential, if it's Holder continuous, then you have positive results. So, as I say, there are many, many people working in thermodynamical formalism who dedicate their whole life to studying this problem. So this is a very well understood problem by a number of people, of which I am excluded. Now, the elements of the set 1 to the n are usually interpreted in the applications as spins of individual particles in a statistical mechanical system. And it's, as you, in the case that we're looking at, we have finitely many spins, i.e. the set 1 to n. But it's often important to look at systems with infinitely many spins. So the question is, how should we do it? How should we generalize the theory to infinitely many spins? Well, it seems obvious how to do it. What you do, you say I is now the set of all spins, and say a countable number, which I'm going to identify with the natural numbers. And then we now take a matrix indexed on the set of spins, i.e. the set capital I, and that's going to be an infinite by infinite matrix of zeros and ones. And we build the Markov space as before. So now the words have letters from a larger alphabet, and again, the adjacency rule is adopted. Now, the trouble is that if we equip I with the discrete topology, it's not a compact space anymore. And therefore, the space I to the n, which appears here, is not even locally compact. An infinite product of non-compact spaces is not even locally compact. So sigma sub A, even if it's closed, is not going to be locally compact. So from this point, if you want to continue that development, you can, but you will have to abandon the tools of analysis, because theorems such as Rist, Titze, Urison, Gelfand, they only hold for locally compact spaces. So the available theory usually goes towards measure theory, and the space sigma A is rather well behaved from the point of view of measure theory, but not from the point of view of topology, because it's not locally compact. So our goal here is to be able to study infinite state Markov spaces without abandoning the tools of topology. So we want a locally compact space. So the question is, how do we fit sigma sub A inside a locally compact space? Now, let me take a detour and talk about algebras, which I understand a little better. And so these are the Coons-Krieger algebras, which are very relevant to the problem at hand. So suppose we have an infinite dimensional Hilbert space H, and we choose an integer n. So we all know that any infinite space can be split in as many pieces as you want. So take H and split it as a direct sum of n subspaces, all of which are separable and infinite dimensional. Then let's take our matrix A with entries in 0, 1, and for each row of the matrix, for each I, let's add the spaces that we see here, but only those for which the entry aij is equal to 1. So unless a row of A is identically equal to 0, which is something that I would like to avoid, these spaces you see here are, again, separable infinite-dimensional spaces, so they are isometrically isomorphic to the original HIs. So let's choose an isometry Si there. So here's an example. Here's a matrix of zeros and ones. So I build my spaces like this. So relative to the first row of matrix, I take the sum of H2, H3, and H4. And as you can see, every time I see 1 up there, I put the corresponding space H here. So these spaces are isometrically isomorphic to the corresponding HIs. So we get 4 operators. Now, if we, those SIs, backing up a little bit, those SIs, they're only defined on the sum, but if we extend them to be 0 on the orthogonal complement, we get operators which are defined on the whole space, and so we get a family of bounded operators on our original space satisfying these relations. These are algebraic relations which are satisfied by these operators. So we come now to a very important concept, which is the Coons-Krieger algebra, which is usually denoted OA. So this is a C-star algebra generated by a family of operators satisfying these relations in a universal way. So you might have noticed the indefinite article here is a C-star algebra. And so I don't really want to go into the definition of exactly what is the, what is the algebra, but it is a C-star algebra generated by operators like that. So most of the time, especially if the matrix is irreducible, you can take that algebra generated by those SIs up there as a model for the Coons-Krieger algebra. Now, if we take a finite word alpha in the letters, we're back in the finite alphabet case, of course. Let's look at the operator, at the element of the algebra OA called S sub alpha, which is just a product of the SIs we had before according to the letters of alpha. And then you can prove that the elements of the form S alpha star, so we take finite words. For each finite word, we have an operator. For each such operator, we look at S alpha star. This turned out to be a family of pairwise commuting projections. And so they generate a commutative subalgebra inside of OA, which I'm going to call D sub A. By Gelfand's theorem, D sub A is isomorphic to the algebra of continuous functions on some space X. And I ask you to guess what is the topological space which is relevant in that situation. It couldn't be anything else but sigma sub A. And in fact, the natural isomorphism between that's given by Gelfand between dA and the continuous functions on sigma of A sends those operators there to the characteristic function of this corresponding cylinder inside of sigma A. So you may view the continuous functions, if you identify the continuous functions with dA inside of OA, and if you define the operator S to be this sum of the SIs, then there's a very interesting commutation relation which says that SF is equal to F composed with sigma. Sigma here is the Markov shift times S. So in a sense, we have that inside of this algebra OA, we have an algebraic encoding of the Markov shift. So let's now take a leap forward and let's consider infinitely many indices. So let's go back to a matrix of zeros and ones called A. So if A is row finite, a matrix is said to be row finite if in every row there are finitely many non-zero entries. If a matrix is row finite, then Kumjian, Pask, Reber, and Renault in 1997, they were able to study a generalization of OA in which the corresponding Markov space, which happens to be locally compact under the special hypothesis, and the theory is very well, works very well. Now, in the general non-row finite case, there is no reason for sigma A to be locally compact. And so we, working with Marcelo Laca some time ago, we were able to figure out a way to deal with these algebras for general non-row finite matrices. And this is what I'd like to try to explain to you briefly. So this is not the way these algebras were first introduced, but I'm going to do a detour and give you a different presentation of this algebra. So now, starting with the algebra, with the matrix A, let's look at the space sigma A, as we discussed a while ago, this non-locally compact space, but I'm not really interested in that because I'm only looking at sigma A as a set. So I look at L2 of sigma A. This is a certain, a strange thing because sigma A is an uncountable set. So I'm looking at the Hilbert space over an uncountable set. So this is a non-separable Hilbert space. But that's no big deal because inside that space we're going to look at algebras generated by countably many elements which are separable. So let's build operators on this huge Hilbert space as follows. For every I meaning here one of the symbols in our alphabet, let's take the canonic basis vector delta sub omega to delta I omega, of course, only when I omega is an element of our shift space. Otherwise, we simply throw the towel and say that the vector goes to 0. As before, for every finite word on this infinite alphabet, we can build these operators S alphas. And it's possible to prove that the S alpha star, just like before, generated commutative C-star algebra, which I'm again going to call dA. And so every commutative C-star algebra by Gelfand's theorem is the continuous functions on a space called the spectrum of the algebra, and what the space is. So this cannot be Markov space because Markov space is not even locally compact, and the spectrum of an algebra is compact. So the point is that dA is continuous functions on a space which I'm going to call XA from now on, which is a sort of an alternative, the alternative that we propose for the badly behaved Markov space sigma sub A. So I'd like to briefly describe to you, so the space is already described, right? The space is described. I have a commutative algebra, and the space is the spectrum of this algebra. But it's not always easy to see what the spectrum of an algebra is, so here is one way to view those elements. So in order to do this, I have to introduce the free group generated by the alphabet. And so for every infinite word in the Markov space, the classical Markov space, I am going to build a subset of the free group. So this is a sort of a leap from the standard point of view. For every word, I'm going to build a subset of the free group on the edges. So this consists of the river formed by all the prefixes of the word omega and including its river basin. If you don't know what a river basin is, so here's an idea of what a river basin looks like. But that's not exact. Maybe there's some element in that space that looks like this river basin. But it actually should be viewed like this. So this is a free group. Unfortunately, I would have trouble drawing the free group on infinitely many generators. So I am asking you to view the free group on 2 generators as a representation of a free group on infinitely many generators. So the word omega, remember that for every omega in the Markov space, we want to build a subset of the free group. So the word omega here is, first of all, this this is the Cayley graph of the free group, and this is the edge A, and this is the edge B. Okay, edges are oriented downwards. So the word I'm talking about is B, A, B, B. So from 1, let's look at the river formed by the word. right? So this is a subset of the free group. But this river also will have tributaries. Every time you have a word in the Markov space which you can attach, say you begin here. If the word that begins here and goes like this and flows into the main river, if that word is in the Markov space, then you paint that black. Okay? So it takes a while to get used to this point of view, and I'm happy to answer any quick questions about this. So the point is, we start with the river given by the word omega, and then we stick in all of the tributaries, and the rule which tells you which tributaries you are allowed to add is simply that wherever you start, if you keep walking and recording the edges that you have traveled, this is supposed to form an admissible word according to the shift. And you do that every time you can do it. So it turns out that for every omega in the classical Markov space, we built a subset of the free group, which I'm representing here as a 0, 1 vector. Now, 0, 1, as opposed to the alphabet, 0, 1 is now a compact set. And the product space 0, 1 to the F is a compact set by Tikhonov. So we are now beginning to put sigma A inside of a compact set. One interesting observation is that this river basing is invariant under translation by the group. It's not actually invariant because the river basing always has the unit of the group. If you translate, you may miss the origin. But the point is that if you do any translation which takes one of the black points to the origin, then the new element will be a river basing for another element of the group, which will be tail equivalent to the original guy. So the theorem that we have in this 1999 paper is that the spectrum of the algebra, the dA, is naturally isomorphic to the closure of that space sigma A within the compact space 0, 1 to the F. So XA is a sort of a compactification of sigma A in the sense that sigma is a dense set according to this map. And so it's very interesting to analyze how do the new elements, the elements that show up in the closure, how do they look like? So they also look like river basins. There's a river and everything that you can add, making of admissible words. But the novelty here is that the main river is not necessarily infinite anymore. The main river may dry up. So you get sub-elements which look like river basins of rivers that eventually dry up. And there's one possibility that the river is dry at its very source. So there's the basing flowing into the unit of the group, and then it does not flow any longer because the river is dry at this point. Oops. So let's look at the subset of the space XA consisting of all river basins except those very dry ones which die at the origin. U is going to be the subset formed by the river basins which flow at least a little bit after the unit. So the generalized shift map is going to be defined only on this subset U, and it's defined as follows. Given any element xi in U, xi is a river basing, so it has a river which has a positive length. So you look at its length is going to be bigger than 1, and so you look at the first edge of the river and you translate it. So this translation will be another element of the space XA, and that defines the generalized shift. And the proposition is that sigma is a local homeomorphism which extends the Markov shift sigma on sigma sub A. Now, Jean Renault, who is actually present here in the audience, has realized that our construction is subsumed by this map, this shift. So he realized that this local homeomorphism encodes all of the relevant information for building the Coons-Krieger algebra, and he showed that this algebra is the generalized Diacono-Renault groupoid associated to this map sigma, and I want to give you some details on that. But before that, let me say that since we first published this paper in 1999, we felt like this should be relevant to people studying thermodynamical formalism, and we have been trying to push this idea, and without much success, until early this year, when I was in São Paulo by invitation of Rodrigo, and we have what I'm going to tell you now is what we have discovered. So here's the definition of the Diacono-Renault groupoids. So that's works very well in the abstract setting of having a local homeomorphism defined on an open set of a space X. And so we build the semi-direct product groupoids, which is formed by triples, in which I forgot to say, so this groupoid is formed by triples, where X is an element in the domain of sigma n. Now we have to be careful now, since the shift is not globally defined, we have to keep track of the domains all the time. So in particular, we can speak of the domain of sigma sub n, which is a set of all elements where you can iterate at least n times. So take the triples, x n minus m y, such that x is in the domain of sigma n, y is in the domain of sigma n, and sigma n x is equal to sigma m y. So if you know the definition of the transformation groupoid, you should look at this equation at the end here as if it said that sigma n minus m of x is y. Right? You cannot say that because sigma is not injective. But if you erroneously brought sigma to the minus n here, then you have the impression that the integer n minus m is mapping x to y. Now, if you start with a potential, and the potential now need only be defined on U, then one can define a one cocycle on this groupoid by this formula. A one cocycle on a groupoid is simply a homomorphism into the real numbers. And this one cocycle induces a flow on the groupoid C-star algebra by that formula. Alpha T of f is essentially multiplying the function by the exponential of the cocycle. So this gives a flow on the groupoid C-star algebra. And a problem that's very important is to compute the KMS states on the groupoid C-star algebra for this flow. And this, every time you have a flow on a groupoid given a cocycle, there's a standard result in Jean Renault's thesis, which says that the measures, if you take if you choose just a measure, if you take a measure on X and you define a state on the groupoid C-star algebra by this formula, simply integrating the function over the unit space, you get a KMS state even only if the measure is quasi-invariant with respect with the correct Radon-Nikodym derivative. In order to give you an easy and direct definition, here is the formula. So what we want to do is, every time we have a function in the groupoid, we add up the function over the inverse image of the range function of the groupoid, and then we integrate over the measure on the unit space. So this defines a measure that I'm going to call nu r on the groupoid G sigma, and likewise, adding the function over the inverse images under the source map and integrating against mu, we get another measure called nu s. So mu is a measure originally defined on the unit space, and we lift that measure up to the groupoid in two different ways. And we say that mu is quasi-invariant if these two measures lifted up to the groupoid are equivalent to each other. And every time you have this phenomena, the Radon-Nikodym derivative of one measure with respect to the other is a measurable cocycle on the groupoid. And Renault's result, which I refer to here, says that the state phi mu, given by integration against mu on the unit space, is a KMS state at inverse temperature to beta, even only if the measure is quasi-invariant and the Radon-Nikodym derivative is precisely the exponential of the cocycle multiplied by the inverse of the temperature. So here is a result which is reminiscent of lots of other known results, but I think it hasn't been proved in that level of generality. And it says that the following three conditions are equivalent once you start with this very basic idea of a local homeomorphism defined on an open set. So the first one is that the state I showed you is a KMS state on that groupoid sister algebra. 2, mu is quasi-invariant with the correct Radon-Nikodym derivative, and the equivalence between 1 and 2 is Renault's theorem. And now 3 is the condition that says that the mu is a fixed point for the Ruelle operator defined precisely by the same formula, except that now the Ruelle operator is only defined on the continuous functions on compact support on U rather than X, because sigma is only defined on U. And the fourth condition says that mu satisfies the Denker-Urbansky condition, which says that the measure that you get, normally measures travel forward through functions, right? Functions act on measures in a forward way by composing the measure with the inverse of the function. Now, in that case, we define a measure going the other way. So mu circle sigma is the unique measure on the space U such that mu sigma of E is equal to mu of sigma of E whenever sigma is injective on E. So the condition is that the new measure we get is absolutely continuous with respect to mu with that derivative. Okay, so here's an example. And the novelty of what I want to tell you is precisely residing on this example. So this is called the renewal shift. This is an infinite matrix, right? And you see it looks like the matrix of the unilateral shift with the first row of ones. The graph associated to this matrix is that. So from any point, you are forced to come back slowly. When you get to 1, you have finally an option of what to do. You can jump everywhere you want. Once you jump, say, from 1 to 6, then you are obliged to come back to 5, 4, 3, 2, 1. And then when you're here, you have options of what you do. So note that this matrix is not row finite because it has a row of infinite, with infinitely many ones. So in that case, the Markov space, the classical Markov space, is not locally compact. But since this matrix, the lack of row finiteness of this matrix is under control, it's easy to describe this, the elements, the new elements that show up in this space XA. So we get only one river basing with a totally dry river, and for every finite admissible word ending in 1, we get another river basing with a finite river, which is precisely translating this perfectly dry river by omega. So this new element flows, the river flows along omega and stops as soon as omega stops. So what we get is that the whole space XA consists of the classical space sigma A plus a countable number of points. And the countable number of points are precisely the ones I just described. This dry river together with this translates. So one thing that we are somewhat excited about this is that people studying quasi-invariant measures or conformal measures on sigma of A, they would only see the measures in this formalism which vanish on YA. So we thought maybe we can find examples in which the conformal measure is living entirely in the new part of the spectrum. So this is what I'm going to try to describe. So we choose a potential H equal to 1, and let's look for conformal measures vanishing on sigma A. So YA is a countable set, so measures there are defined by the values of the measure at each element. And if you look at any one of those conditions, for instance, the Dankler-Urbanski condition, the condition says that the values of the measure on the sets has to satisfy these conditions. And then it's easy to solve the equations. And this is the solution of the equation. Of course, we need to normalize the measure. And so we have to choose the appropriate value of k. And doing so, you simply have to add all of the numerators and make sure that that's 1. Sorry, we need to add the numerators and put that as a denominator to get a probability measure. And you see that after a quick computation, this is what you get. So this is a power series on e to the ln of 2 minus beta. And this is going to be convergent even only if beta is bigger than log of 2. So this, for every beta bigger than log of 2, we get a conformal measure which is entirely supported on YA, which is the piece which is invisible to the classical theory. So if you want to see this new conformal measures, you have to look outside sigma of A. And what's interesting is that in the classical case, it was known that there is a single conformal measure for every temperature, and now we have for beta bigger than ln of 2, there is one more, which was previously unknown. Okay, now we were looking at various conditions which were all equivalent to each other. In particular, the KMS condition, the conformal measure condition, and the quasi-invariant conditions are all equivalent. And this was regarding the entire Renault-Diacono groupoid. Now, the Renault-Diacono groupoid, if you remember right, was the set of all triples which had an integer number in the middle. So I want to look at the subgroupoid formed by the triples which have a 0 in the middle. So an element of the form xy0 is in that subgroupoid, even only if y and x have the same image under the same power of sigma. And so this brings in an equivalence relation which is defined on the domain of sigma sub n. So we say that x and y are equivalent under this equivalence relation Rn, even only if sigma n is equal, sigma nx is equal to sigma n y. Now the trouble is that these equivalence relations, they are defined on smaller and smaller sets. Now, a notion that Renault has worked in the past is the notion of approximately proper equivalence relation. So let me just give you this definition, which is quite relevant here. So an equivalence relation on a topological space is said to be proper if the quotient space is Hausdorff and the quotient map is a local homeomorphism. When you have such a thing, you can look at R as a groupoid, and this groupoid becomes an étale groupoid with the topology inherited from the product topology on X cross X. And again, Renault defined an equivalent relation to be approximately proper if it's the union of an increasing family of proper relations. And Renault has studied these relations, these groupoids, in this paper in 2005. But the situation here is different because we have two complicating factors. First of all, since the relations are on the set, on the U's, they are no longer compact, so we must work with these relations for non-compact space. A very complicating factor is that a proper equivalence relation on a compact space has finite equivalence classes. And here, they can have infinitely large equivalence classes. So the other difficulty, as I said, the relations are defined on different spaces. So this is an idea. This is an abstraction of the former idea, which we are going to call a generalized approximately proper equivalence relation on a space X. So X is a given space. So this object consists of a collection of open sets of open subsets of X, which are decreasing, and the Rn's should be proper equivalence relations on the UN's, and we want the relations to be increasing. That's we want to try to mimic what Renault does, but they cannot be increasing if they are defined on smaller sets. So the crucial point is that this equation here, Rn, which is a set of pairs, intersection UN cross UM should be contained in Rm for every m. So this is a generalization of the notion of increasing relations, and of course R0 should be the diagonal. So this mysterious relation, axiom 2 here, essentially says that the Rn's are increasing as long as you restrict to the subset, right? So if you restrict Rn to Um, then you get a relation which is dominated by Rm. Another interesting thing is that every Um is invariant under every relation Rm, in the sense that if a point in Um is equivalent to a point in Um under the relation Rn, then the X must be in Um. Time flies, so I have to speed up a little bit. And so given U and UN and Rn as above, we can look at the union of these equivalence relations. And this turns out to be an equivalence relation again. And it's an étale groupoid with the inductive limit topology. And so in order to put a cocycle, we start with a sequence of potentials. And those are functions defined on the spaces UN for every n bigger than 1. And there's an important axiom here saying that each Kn should be invariant under the previous equivalence relation Rn minus 1. And then you can define a cocycle using a similar formula. And these cocycles, which are defined on each Rn, admit a common extension to R. And we once again want to determine the KMS states on this on the C-star algebra of this groupoid, or according to Renault's result, the quasi-invariant measures on X. So the interesting point is that since R is the union of the Rn's, this is the same as saying that the restriction of the measure that we're looking for is quasi-invariant over every Rn. So this brings us to the problem of analyzing the quasi-invariant measures for a single proper equivalence relation, which is something that Renault has done in this 2005 paper in the compact case, which we cannot use here because our equivalence classes are infinite. So let's go back to a much simpler situation that we had before. Simply look at a locally compact space with a proper equivalence relation, and look at the groupoid associated. So given a continuous function, we have a cocycle, and with this cocycle, we introduce this condition expectation, this object that looks like a condition expectation, which averages the function on the equivalence classes, which are now infinite. But as long as we sum, as you apply this only to functions with compact support, the sum is going to be finite. So this is well defined and gives us a continuous function. Now, that's what I just said, that the sum is finite. Now, if we take the function the constant function 1 and apply this formula to 1, we get the partition function, as we call it, which is simply the sum. And that is no longer known to be finite, and it could very well be infinite. And so we work with this function, and we come up to this theorem that gives conditions for, I can't go forward. Yeah. So we get the conditions for the measure to be quasi-invariant, and they look a bit like the study of DLR measures. So I see that the clock is ticking, and I have to, maybe I should finish here, and simply making the observation, the important observation, that the quasi-invariant measures are obliged to vanish on the space where the partition function takes the infinite value. 4, 3, 2, 1. So thank you very much.
Thank you very much, Professor Exel. Are there any questions?
Can you say, you said with this row of all ones, with the matrix with the row of all ones, you said there was one river basin that just completely dried up. Can you describe that in terms of the infinite paths? Like, can you tell us what it is quickly?
Yes. So look at the infinite path. Starting from 1, you may jump to every point that you like. Mm-hmm. So jump to the point n and continue infinitely many times in any way you want, and call that word Wn. Okay? So choose one word, one infinite word Wn, which begins by jumping from 1 to n. And then you can continue that as you like. So this is a sequence of functions inside this compact space. So it must have a accumulation point, right? And this accumulation point, it doesn't know exactly which is the first step it's going to take, because as long as you are over n, then the n is, so the dry river is the limit of a sequence of rivers which go to the other places. Now the basin, the river basin that you see behind you, stays fixed because of the rules forming. So that's, if you take any infinite path starting at 1 and you look at its river basin, then all you have to do is erase the forward path, and what you look back, that's the finite path. That's the basin.
Any other questions?
In your example of the renewal, do you get all the KMS states of the algebra of the automorphism group?
So as I said, I mean, I have two disclaimers before I answer your question. First of all, this is work in progress. Second of all, I am not a specialist, but let me try to say what I believe is true. In the classical study of sigma A, Sarig has shown that there exists one conformal measure for each beta. But that's on sigma A. Now, we have now seen that because of the series that diverges on the wrong side of the axis, there is no conformal measures living in this exceptional set for beta less than log of 2. So for beta less than log of 2, apparently the only conformal measure is the one that Sarig already knows about. Now, on the other side, for beta bigger than 2, we have, so the measures are the ones that Sarig already knew. That's unique for every temperature. But then we have this extra measure. So it looks like the classical theory did not see a phase transition. But once you look to this enlarged space, you see a phase transition in the sense that at ln of 2, you have a change in regime from a single conformal measure to two extreme conformal measures. So that's what I think, and that's what we're trying to figure out. And Rodrigo here is saying yes, so.
Thank you.
Any other questions? I have a question. Since one of the most interesting results, in my opinion, about phase transition is the so-called Lee-Yang theorem, which deals with zeros of the partition function. Do you have any idea about the zeros of the partition function? They proved, actually, that in the classical case, the zeros of the partition function are purely imaginary. And this is one of the classical results in, well, it's very much related to zeros of entire functions and some other stuff I've been interested. Have you tried to check anything about the zeros?
What has become very relevant to us here is the places where the partition function is infinite. But our partition function is bounded below by the if I could come back here to the definition of partition function.
Lee and Yang considered the partition function as a function of somehow of a complex variable.
Yeah.
And they proved that the zeros are on the imaginary axis.
Right. But this, this partition function is defined on a Cantor space. It's not the case of a partition of the continuous case. So it's not easy to see exactly what kind of an extension you can get.
And right now we just are able to do this for particulars depending on the first coordinate. In the easy model is much more complex, the energy function.
I see. Thank you. Any other questions? Let's thank. Oh, okay.
Show us the last 3 slides.
Okay, that gives me the opportunity to. So in the last 3 slides, in this slide, it's just several conditions. One interesting condition that shows up here is the 4, and in this slide, I was trying to understand exactly what is this condition. So I'm describing more carefully the condition 4, which I repeated here. And so what I'm introducing a new operator, f beta, which is what you see here. And viewing this explicitly with all of the definitions involved, this looks like the Gibbs function, because it's just e to the beta divided by the partition function. The partition function may be infinite, so the inverse may be 0, and we have no problem with that. And so this f beta turns out to be a conditioned expectation. So what we actually need is that the measure mu should be fixed under this conditioned expectation, which is reminiscent of the DLR measures and averaging over outside finite boxes. And then I was just going to say in which way the Diacono-Renault groupoid example, which motivated this generalization, is related, and how you get the potential from that. And so since a groupoid, you're looking at a groupoid and a subgroupoid, and of course, measures which are quasi-invariant for the big groupoid are necessarily quasi-invariant for a smaller groupoid. So we get, for instance, a result that says that every conformal measure is a DLR measure. And this is just a statement of writing down the statement in full. And in fact, there was a joke. There were some references here. And also, there was a little joke that I had to skip.
Okay, let's then thank the speaker once again for the very interesting lecture.